July 24, 1943, roughly 120 miles west of Truk Lagoon in the Central Pacific. Through a slightly clouded periscope, Lieutenant Commander Lawrence Randall Daspit observed a scene that would ultimately expose one of the most consequential technical failures in U.S. naval history. Centered in his sights was a Japanese tanker of 19,262 tons, immobilized after absorbing 2 successful torpedo strikes that had already knocked out its engines. It was the ideal submarine target, large, stationary, and defenseless. Daspit prepared the finishing attack. From close range and at a near-perfect 90-degree angle, he launched what should have been a textbook final shot, the kind submarine officers were trained to execute flawlessly. Instead of a decisive explosion, what followed over the next hour forced him to confront an unsettling truth. The failure he documented that day would add to mounting evidence that the Navy's primary undersea weapon was deeply unreliable. For more than a year and a half, American submarines in the Pacific had been operating with torpedoes that malfunctioned at alarming rates. Submarine crews risked their lives while Japanese shipping frequently escaped unscathed. Reports of failure were often met not with technical reassessment, but with skepticism directed at the officers who filed them. Yet Daspit's meticulous documentation would become part of the body of proof too substantial to dismiss. At the center of the controversy was the Mark 14 torpedo, the U.S. Navy's standard submarine weapon at the outbreak of war. Developed at the Naval Torpedo Station in Newport, Rhode Island, it represented cutting-edge engineering for its time. Significant, however, was its Mark 6 magnetic influence exploder. Designed in strict secrecy beginning in the early 1920s, the device was intended to detonate beneath a ship's keel rather than on contact with its hull. The resulting underwater blast would create a powerful gas bubble, theoretically snapping a vessel in two by breaking its structural spine. In concept, a single well-placed hit could destroy even a heavily armored warship. Despite the weapon's importance, live-fire testing was remarkably limited. Only 2 such tests were conducted on May 26, 1926. In the first trial, the torpedo failed to detonate after passing beneath its target. The second test succeeded, sinking the decommissioned submarine USS L-8, which had been designated specifically for that purpose. After that date, no additional full-scale live tests were performed prior to America's entry into World War II. Financial and production constraints played a decisive role. The Great Depression had severely reduced military funding throughout the 1930s. At Newport, thousands of workers operated around the clock, yet output averaged only about 1.5 torpedoes per day. By 1938, outstanding orders had accumulated to tens of millions of dollars. With limited supply and high cost, destructive testing was considered impractical. Instead, the Navy relied on trials using practice warheads. These lighter heads allowed torpedoes to float after expending fuel, enabling recovery and inspection. Under these controlled conditions, performance appeared satisfactory. The magnetic exploder was also evaluated in laboratory tanks filled with still water, where results seemed consistent. None struck their targets. Jacobs had tracked one ship for nearly an hour to refine his firing calculations and was confident in his solution. Yet 8 launches yielded no confirmed explosions. Similar reports emerged across the Pacific. As early as mid-December 1941, USS Seawolf indicated that torpedoes were traveling significantly deeper than the depth settings selected by their crews, perhaps 10 to 15 feet below intended levels. At such depths, the magnetic exploder might not detect a ship's field, and contact with the hull would be unlikely. Additional malfunctions followed. Premature detonations were reported within weeks of the war's outbreak. Some torpedoes exploded partway to their targets, others failed to detonate altogether. In rare but alarming cases, circular runs sent torpedoes curving back toward the submarines that had launched them. By June 1942, American submarines had expended more than 800 torpedoes in combat. Approximately 80% failed to produce effective results. The implications were stark. U.S. submarines were expected to cripple Japan's merchant fleet and restrict its logistical lifelines. Instead, convoys often passed through patrol zones with limited losses, while American crews faced enemy counterattacks after failed strikes. Submarine commanders documented each malfunction in detailed patrol reports. They described depth control errors, faulty detonations, and erratic performance. Requests for technical review grew increasingly urgent. Targets, lost opportunities, and lives placed at unnecessary risk. Submarine commanders in the Pacific kept asking for formal trials of their torpedoes. They were convinced something was wrong. The reply from the Bureau of Ordnance was unwavering and deeply dismissive. According to the Bureau, the Mark 14 was not at fault. The real issue, they insisted, was human error. Commanders were accused of poor attack angles, incorrect firing calculations, and improper maintenance. After all, the Bureau had designed the weapon, and the Naval Torpedo Station had manufactured it. Nearly 20 years of research and refinement stood behind the Mark 14's development. From their perspective, it was inconceivable that the defect lay in the torpedo itself. If ships were not sinking, the blame must rest with the men launching the shots. At Pearl Harbor, Rear Admiral Thomas Withers, Commander Submarines Pacific, supported the Bureau's position. When his officers reported repeated failures, he attributed them to insufficient aggressiveness and flawed judgment. Torpedoes were costly and scarce. Expending them on live testing was considered wasteful. The Bureau had certified the weapon as reliable. That officially settled the matter. One senior officer, however, was not convinced. Rear Admiral Charles Andrews Lockwood had spent most of his career beneath the surface. Born in Midland, Virginia, in 1890, he graduated from the United States Naval Academy in 1912 and entered submarine service 2 years later. By the end of 1914, he was already in command of USS A-2, one of the Navy's earliest submarines. There he encountered alarming reports: torpedoes missing clean shots, striking without detonating, or failing entirely. Japanese vessels were escaping attacks, while American submarines risked destruction for negligible results. Lockwood understood that the Bureau would not authorize large-scale testing. Inventory was limited, and each torpedo carried significant cost. Yet he judged that sending crews into combat with unreliable weapons was far more dangerous than sacrificing a few rounds for investigation. In June 1942, without approval and fully aware of the professional risk, he ordered independent trials of the Mark 14. Under the direction of his Chief of Staff, Captain James Five, a straightforward experiment was arranged in Frenchman Bay near Albany. Fishing nets were suspended at precisely measured depths. On June 20, USS Skipjack launched a torpedo set to run at 10 feet. Fired from 850 yards, it should have pierced the net at that depth. Instead, it tore through at approximately 25 feet, 15 feet deeper than programmed. Additional shots on subsequent days showed similar deviations, consistently exceeding their settings by about 11 feet. The conclusion was unmistakable. The torpedo was running too deep. Lockwood forwarded the data to the Bureau of Ordnance. The response dismissed the findings as methodologically unsound. According to the Bureau, the net system lacked scientific rigor, and any discrepancy likely resulted from improper adjustments by submarine crews. Lockwood repeated the trials, achieving nearly identical results. Had entered the wall, the Bureau of Ordnance formally acknowledged that the Mark 14 consistently exceeded its depth setting by roughly 11 feet. Investigation revealed layered design shortcomings. During development, tests had used lightweight practice warheads. In combat, however, the torpedo carried a 680-pound explosive charge, altering its balance and buoyancy and causing it to sink lower than intended. Compounding the issue, the depth control system relied on a pressure sensor installed in the torpedo's tapered tail section. At high speed, around 46 knots, the flow of water around that shape generated reduced pressure, misleading the sensor into reading a shallower depth than actual. The mechanism responded by directing the torpedo downward. The faster it traveled, the deeper it ran. A single full warhead trial during development could have revealed the flaw, but such a test was never authorized due to cost. Corrective calibration procedures were issued in August 1942. Submarine captains compensated by setting depth controls near zero to offset the established error. For a brief period, it appeared the crisis had been resolved. It had not. With depth settings adjusted, another defect became impossible to ignore. Torpedoes began detonating prematurely, erupting harmlessly in open water before reaching their targets. The magnetic influence exploder was triggering too soon. The struggle between field experience and institutional certainty had cost valuable time and nearly cost far more. Subsequent intelligence reviews uncovered a troubling reality. Every one of the 7 torpedoes in that earlier action had detonated before reaching its objective. The magnetic influence feature was activating too soon. Not a single weapon struck its intended target. The same pattern appeared again and again in 1943. On April 10, the submarine USS Pompon launched 6 torpedoes at the Japanese carrier Shokaku. At least half of them exploded short of the hull. The carrier escaped without damage. 2 months later, on June 10th, USS Trigger attacked another carrier from close range. Of 6 torpedoes fired, 1 veered off, 1 blew up prematurely, another failed entirely, and only 2 caused limited harm. The target survived and withdrew. By mid-1943, the evidence was overwhelming. The magnetic exploder was deeply unreliable. On April 27, the Bureau of Ordnance conceded that the Mark 6 exploder was prone to early detonation, particularly in shallow water. Their solution was cautious and conditional. They advised disabling the magnetic function and relying on contact detonation instead, but also proposed extending the arming distance from 450 to 700 yards and limiting firing situations to reduce risk. Admiral Ernest J. King rejected the longer arming distance as impractical. Submarines needed to operate at close quarters. He supported the view of Charles A. Lockwood. The magnetic feature should simply be shut off, be dabbed onto the screws securing the device. Any disturbance would reveal tampering. Officers were forbidden from examining the very equipment they depended on for survival. Submariners, however, were not passive. Torpedomen quietly learned which paint color was used, obtained matching supplies, and opened the mechanisms themselves. After making adjustments, they carefully repainted the screws. When the torpedoes returned to official depots, no visible evidence suggested interference. Across the Pacific, commanders increasingly disabled the magnetic feature without authorization. Patrol reports were subtly adjusted to justify higher torpedo expenditures. For many, the alternative was accepting needless losses. One senior officer stood apart. Rear Admiral Ralph W. Christie, commander of submarines in the Southwest Pacific, had overseen development of the Mark VI in the interwar years. His professional reputation was tied to its success. Despite mounting failures, he insisted his boats continue using the magnetic system. Crews under his authority endured persistent malfunctions, while submarines in Lockwood's theater, operating without the magnetic feature, began achieving tangible results. Only in November 1943, after intervention by Admiral Thomas C. Kincaid, was Christie compelled to follow suit. Even then, torpedo problems did not end. A third defect emerged: direct hits that produced no explosion at all. On July 24, 1943, Lieutenant Commander Lawrence Daspit aboard USS Tenosa encountered what appeared to be an ideal target, a large unescorted tanker identified through code-breaking intelligence. With the tanker immobilized and listing, Daspit maneuvered into an optimal firing angle at close range, precisely the geometry submarine officers were trained to exploit. What followed defied explanation. Torpedo after torpedo struck the hull with audible impact, yet failed to explode. 5, 6, 7, 8. Each hit cleanly and went silent. The torpedo officer confirmed the settings: proper depth, armed contact exploders, no visible mechanical fault. Still, the pattern continued. Additional shots connected without detonation. One weapon even appeared to ricochet, veering away after striking. By now, a Japanese destroyer had arrived and begun dropping depth charges. Before diving to evade pursuit, Daspit launched his remaining torpedoes. Each one hit, none exploded. 15 torpedoes fired, 11 confirmed impacts, only 2 detonations. Daspit retained a single torpedo. Rather than expend it uselessly, he chose to preserve it for technical examination. He set course for Pearl Harbor, recording in his log that he was returning without sinking his target. Tenosa reached base on August 4, 1943, carrying with it the evidence that would further expose the depth of the torpedo crisis. Daspit headed straight for Submarine Force Headquarters. At the entrance, he was received by Charles A. Lockwood, who had assumed command of the Pacific Submarine Fleet in February 1943, after Robert H. English was killed in an aircraft accident on January 21st. Lockwood anticipated an outburst. Recovered by Tenosa, was immediately delivered to the base torpedo facility for inspection. Technicians disassembled and tested it from nose to tail. On paper, everything functioned as designed. No obvious defect could be identified. By standard measures, the weapon should have detonated on impact. Lockwood understood that waiting for the Bureau of Ordnance to acknowledge the issue would be futile. Officials had dismissed earlier complaints about torpedoes running too deep and had long resisted evidence that the magnetic exploder was unreliable. He expected the same resistance regarding contact detonators, unless presented with proof that could not be ignored. Without seeking authorization and risking his own position, Lockwood initiated independent trials. He tasked Commander Art Taylor, his gunnery and torpedo officer, with arranging live-fire tests using fully armed torpedoes under realistic combat conditions. He also brought in Lieutenant Commander Charles B. Mommsen, already well known in the submarine service. In 1939, Mommsen had led the rescue of 33 sailors from the sunken submarine USS Squalus and had developed the Mommsen lung, a breathing device that saved numerous lives. His expertise in engineering and testing made him indispensable. Taylor and Mommsen studied nautical charts of Hawaiian waters to find a suitable proving ground. They required steep underwater cliffs descending into deep water with a sandy floor to allow recovery of test weapons. A remote location of Kahoolawe, southwest of Maui, met these conditions. On August 31, 1943, the submarine USS Muskellunge launched 3 live torpedoes into the rock face. Inspection of the Mark VI exploder revealed the core flaw. The firing pin had been released, but failed to travel far enough along its guide rails to strike the primer with adequate force. The violent deceleration at 46 knots had distorted the mechanism, preventing detonation. Ironically, the more direct and forceful the impact, the greater the likelihood of failure. A perpendicular 90-degree strike, the textbook ideal taught to submarine commanders, was the condition most prone to produce a dud. Since repeatedly firing expensive warheads into cliffs was impractical, Lockwood approved a controlled experiment. Taylor supervised construction of a test apparatus using a crane from the Pearl Harbor Navy Yard. Dummy warheads, weighted with sand to match live explosives, were dropped from 90 feet onto a steel plate set at various angles. The height was calculated so that impact velocity would replicate a torpedo striking at 46 knots. The findings were conclusive. When the warheads hit at a 90-degree angle, roughly 70% failed to detonate. At 45 degrees, the failure rate dropped to about half. Oblique impacts proved significantly more dependable than direct ones. The underlying problem traced back to the firing pin assembly in the Mark VI exploder. It had been engineered for slower torpedoes and was too fragile to withstand the stresses generated by the faster Mark XIV. Training and complicated attack geometry, but it significantly reduced the dud rate. Just as important, the new firing guidance provided practical proof. It demonstrated beyond dispute that the defect was real and could no longer be dismissed. American submarine captains in the early years of World War II were not failing because of poor judgment or lack of skill. The real problem lay inside their weapons. The Navy's torpedoes, specifically the Mark XIV torpedo fitted with the Mark VI exploder, were deeply flawed. Rear Admiral Charles A. Lockwood understood that temporary tactical adjustments, such as ordering angled oblique shots, would not permanently solve the issue. The defect was mechanical. The firing mechanism needed to be redesigned. Yet authority over torpedo design and modification rested with the Bureau of Ordnance, and the Bureau showed little willingness to acknowledge another costly mistake. Faced with resistance, Lockwood bypassed the bureaucracy. He directed the submarine tender USS Holland to begin producing altered firing components. The original exploder used a heavy steel firing pin block. Under the shock of impact, inertia caused that mass to shift and jam the mechanism, preventing detonation. Working under Commander Taylor's supervision, Lieutenant E.A. Johnson devised a practical solution: a lighter firing pin block machined from aluminum alloy. The source of that aluminum carried symbolic weight. It was salvaged from propellers of Japanese aircraft destroyed during the attack on Pearl Harbor. On September 30, 1943, the submarine USS Barb departed Pearl Harbor, carrying 20 torpedoes equipped with the modified aluminum firing pins produced aboard USS Holland. The change in performance was unmistakable. The torpedoes detonated as intended. By mid-October, enough upgraded components had been fabricated to supply submarines heading out on patrol. Nearly 2 years into the conflict, the United States Navy finally possessed a dependable torpedo. The operational impact was immediate. During 1942, American submarines had launched 1,442 torpedoes with disappointing results. Post-war evaluation by the Joint Army-Navy Assessment Committee determined that only 134 enemy ships, totaling about 580,390 tons, had actually been sunk. Far fewer than wartime claims suggested. With reliable weapons in 1944, submarine forces destroyed 492 vessels, amounting to over 2.3 million tons. In 1945, they sank 132 more ships, totaling nearly 470,000 tons. The decline in numbers reflected the near collapse of Japan's merchant fleet, rather than reduced effectiveness. Once corrected, the Mark 14 became one of the Pacific War's most potent naval weapons. American submarines ultimately sank approximately 1,314 Japanese ships, totaling more than 5.3 million tons. Failed at decisive moments. How many crews were forced into repeated attacks when a single successful salvo should have sufficed? How many enemy ships survived long enough to strike back? These uncertainties followed him long after the war. When the torpedo defects were finally resolved in September 1943, Lockwood described the moment as a kind of victory day for the submarine force. From that point forward, American submarines operated as fully effective offensive weapons. Still, he later reflected that if the torpedoes had been properly tested before the war, combat would have begun with functioning arms, the conflict might have ended sooner, and lives could have been spared. The Bureau of Ordnance never issued a formal apology. Its post-war review admitted inadequate testing and flawed production planning. Officials acknowledged that the torpedo had been designed for limited peacetime manufacturing, unsuitable for rapid wartime expansion. Their final report conceded that much of the corrective work undertaken after 18 months of war should have been completed in peacetime. The failure to question design shortcomings, either in Washington or at the Naval Torpedo Station in Newport, reflected a serious lapse in practical judgment. As a corrective measure, the Bureau declared that no future torpedo would be adopted for service without testing under realistic combat conditions. The torpedo controversy exposed systemic weaknesses in the Navy's weapons development process. Budget constraints had outweighed combat effectiveness. Secrecy prevented operators from understanding the devices they relied upon. Institutional pride delayed reforms even after field commanders identified problems within weeks of entering the war. For a long time, senior naval officials refused to acknowledge that the Navy's newest torpedo suffered from fundamental engineering defects. Instead, they placed the blame on submarine captains, suggesting poor seamanship and faulty tactics were the real causes of repeated failures. Even when evidence mounted, the institution resisted change, opposing adjustments, redesigns, and even further investigation. Into this conflict stepped Charles A. Lockwood. He was not celebrated for technical brilliance, but for something rarer in a rigid bureaucracy. He trusted the officers in combat. He took their reports seriously. When formal channels stalled, he authorized independent trials. When paperwork blocked progress, he moved around it. Though torpedo design was not his official responsibility, he assumed personal accountability for solving the problem. Most critically, he refused to continue sending crews into battle with weapons he believed were unreliable. In June 1942, his unofficial tests at Frenchman Bay demonstrated that torpedoes were running deeper than their set depth. In August 1943, further unauthorized trials at Kahula exposed the failure of the magnetic detonator. By September 1943, aboard the submarine tender USS Holland, field modifications were implemented that finally produced dependable results. Each step challenged regulations, each action risked disciplinary charges, and each decision directly confronted the Bureau of Ordnance, one of the Navy's most powerful institutions. Submarine force destroyed more Japanese shipping than all other American forces combined. The once troubled Mark 14 torpedo had become one of the most feared weapons in the Pacific. Its eventual effectiveness, however, traced back to one officer's refusal to accept institutional complacency. At its core, the torpedo controversy was a failure of testing. In 1931, a new automobile cost roughly $700. A single Mark 14 torpedo cost $10,000. Concluding that live tests were too expensive, the Navy relied on exercise heads instead of full warheads, evaluated the magnetic detonator in laboratory tanks, and conducted only 2 live fire shots back in 1926. After that, the weapon went into mass production and then into war. The consequences were severe: missed targets, submarines exposed to counterattack, lost crews, and a prolonged conflict. By 1944, American factories were turning out 150 Mark 14 torpedoes daily, with total wartime production surpassing 60,000 units. At 1930 prices, that represented roughly $600 million, about $12 billion in modern terms. Proper pre-war testing would likely have required only a few dozen full-scale firings, perhaps costing $500,000 in 1930, less than the price of a single submarine. The arithmetic is stark. The price of inadequate testing was measured not only in money, but in time, lives, and the length of the war itself. The Pacific War might have taken a very different course had a critical flaw been addressed before the first shots were fired. In 1939, a relatively small investment, around 50 torpedoes expended in realistic sea trials, costing roughly $500,000, could have exposed serious defects. That modest expense might have spared tens of thousands of lives and saved billions in wartime losses. Instead, the U.S. Navy's Bureau of Ordnance concluded that such large-scale testing was too costly. The true cost, however, came from failing to test at all. Today, the torpedo crisis is examined in military academies as a classic warning. It underscores several enduring principles. Weapons must be evaluated under authentic combat conditions. Laboratory simulations and inert warheads cannot replicate the chaos of battle. Those who rely on the equipment, especially front-line commanders, must have a voice in its development. Submarine captains identified torpedo malfunctions within weeks of America's entry into the war, yet they had not been meaningfully involved in the design process. Institutions must also possess the humility to acknowledge error. For nearly 2 years, the Bureau resisted mounting evidence from the field. Excessive secrecy compounded the problem. The magnetic exploder mechanism was classified so tightly that even submarine commanders were barred from inspecting it, preventing experienced operators from diagnosing its defects. Above all, effective leadership demands trust in expertise and the willingness to confront entrenched authority. 3. American submarines were finally equipped with dependable torpedoes. The change in performance was immediate. Submarines that had previously endured patrol after patrol of frustration suddenly became formidable. Under Commander Richard O. Kane, USS Tang achieved extraordinary success. USS Barb, benefiting from modified firing mechanisms first implemented aboard USS Holland, built a legendary combat record of its own. American submarines fanned out across the sea lanes surrounding Japan, the Philippine Sea, the East China Sea, and beyond, targeting tankers, cargo vessels, troop transports, and warships. Japan's war machine depended on maritime supply. Oil from the Dutch East Indies, rubber from Malaya, and food from Indochina all had to cross vast stretches of ocean. Once U.S. submarines possessed reliable torpedoes, those routes became perilous. By 1945, Japan faced crippling shortages. Factories lacked raw materials, cities struggled with food scarcity, and the military confronted severe fuel deficits. Submarines accomplished what bombing campaigns and surface engagements alone had not fully achieved. They severed the logistical lifelines that sustained the Empire's capacity to fight. The Mark 14 torpedo, initially plagued by malfunction, remained in service until 1980, improved and modernized over decades. Yet it would never have become an effective weapon without Lockwood's determined inquiry. His investigation, conducted despite institutional resistance, validated what crews already suspected: the weapons were failing. More importantly, he acted decisively to correct them. Lockwood died on June 6, 1967, at the age of 77. Yet his defining achievement did not occur in a fleet engagement. It took shape in test ranges, manufacturing adjustments, and contentious meetings in Washington. It was forged in his willingness to heed submarine commanders' reports and to prioritize their safety over bureaucratic comfort. His legacy rests on a simple but demanding principle. When lives are at stake, leadership requires the courage to question authority, to investigate what others prefer to ignore, and to correct flaws no matter the institutional resistance. That resolve is how one admiral restored America's torpedoes, and in doing so, reshaped the course of the war at sea.